All right, let's talk about Rust. It's a programming language that's been making some serious waves, and for good reason. It has a really unique take on how to build software that's both fast and super reliable. So let's just dive right in. For the longest time, if you were a developer, you had to make this tough choice. Do you go with something like C++ for that raw, metal-to-the-pedal speed, but then you have to constantly worry about these nasty memory bugs? Or do you pick a language like Python or Java, where the memory is handled for you, but you often take a hit on performance? Well, Rust comes along and asks a really simple but powerful question. Why can't we have both? And it looks like a ton of developers are totally on board with that question. A great way to see this is by looking at Rustlings. It's this super popular way to start learning the language. Its main repository has, get this, over 62,000 stars on GitHub. Now that number isn't just about hype, it's a signal. It tells you there's a huge, vibrant community building amazing resources. This is definitely not some niche thing, it's a full-blown movement. So what is all the fuss about? What's pulling so many developers into the world of Rust? Well, it really all comes back to that one core idea, finally solving that old headache of performance versus safety. Think of it like this. For ages, programming was kind of split into two teams. On Team 1, you've got languages like C++ with manual memory management. This gives you insane speed and control, but it also means you could accidentally cause some really difficult-to-find bugs like seg faults. Then on Team 2, you've got languages like Python with automatic garbage collection. It's way safer, for sure, and easier to manage, but that safety net often slows things down. Rust's whole mission is to just make that trade-off disappear. Okay, so you're interested. Where do you even begin? This is something the Rust community has thought a lot about. Instead of just tossing you into the deep end, they've created this amazing tool called Rustlings. And just to make the whole experience feel a bit more welcoming, you're greeted by Ferris. He's the adorable, unofficial crustacean mascot for Rust. It's a small thing, but it kind of shows you that this is a community that really cares about making learning fun and approachable. The whole idea behind Rustlings is just brilliant. It's not about memorizing dense theory. It's a bunch of small, interactive exercises that are designed to build up your muscle memory. You're basically given little broken programs, and your job is to fix them. As you do, you start to naturally absorb the core concepts of the language, one step at a time. So for anyone out there whose curiosity is piqued, this is the place to start. It's this great interactive tutorial right in your command line, and it's pretty much the gold standard for anyone new to Rust. So, how does Rust actually do it? How does it give you memory safety without that performance-killing garbage collector? The secret, the real magic, lies in its most famous feature, something called ownership. In a nutshell, ownership is a set of rules that the Rust compiler enforces. And here's the key. It checks these rules when you compile your code before it ever runs. It figures out exactly when and where memory should be cleaned up. That means you get all the safety benefits, but with absolutely zero performance cost when your program is actually running. And it all boils down to these three surprisingly simple rules. First, every single piece of data has a variable that owns it. Second, there can only be one owner at any given time. No sharing ownership. And third, when that owner is no longer needed, like when a function finishes, the data it owns is automatically cleaned up. Simple as that. Okay, I know that can sound a little abstract, so let's actually see what this looks like in practice. We'll walk through a quick visualization to see how these rules protect you. Okay, first up, we create a variable called t. Pretty straightforward. That variable now officially owns the value s of 1. So according to rule number 1, t is the one and only owner. Now, what happens if we try to assign t to a new variable a? This is where rule number 2 comes into play, and it's a huge deal. The ownership is moved from t to a. The data isn't copied, ownership is just transferred. And because of that, the compiler now considers t to be invalid. You literally can't use it anymore, which prevents a whole class of bugs right there. But what if you just want to let some other code use the data for a little while without giving up ownership? Well, that's what references are for. You can think of it as borrowing. Here, R is a reference that borrows the value owned by A. It can see the data, it can read the data, but it doesn't own it. And this is where we see the true genius of Rust's borrow checker. Let's say we have a reference that's borrowing the variable B. If some other part of your code tries to change B while it's being borrowed, nope. The compiler will stop you cold. It won't even let you build the program. This one feature completely eliminates a dangerous type of bug called a data race, and it all happens before you even hit run. So we have this incredibly powerful system that gives us both performance and safety. That's great, but what can you actually build with it? The answer, it turns out, is just about anything you can imagine. I mean, just look at how broad this ecosystem is. You want to do web development? You've got blazing fast frameworks like Axum and Actix. You're into game development? Engines like Bevy are doing some incredible stuff. It's also fantastic for building really fast and reliable command line tools. Heck, you can even use it for WebAssembly, which means you can run Rust code safely and efficiently right inside a web browser. So what's the big picture here? Well, you get performance that can go toe-to-toe with C++, which is perfect for web servers. You get rock-solid memory safety, which is absolutely critical for things like operating systems or code running on tiny embedded devices. And on top of all that, you get Cargo, which is probably one of the best package managers and build tools out there. It just makes everything so much easier. And that brings us right back to where we started. Even with all this incredible power under the hood, the community makes getting started a top priority. It really fosters this culture that believes powerful tools don't need to be impossible to learn. And it all starts with those small, achievable steps. So I'll leave you with this final thought to chew on. We usually think of constraints as being, well, constraining. But what if a compiler that guarantees your code is memory safe isn't a limitation, but is actually a form of liberation? By completely taking away entire categories of bugs that you'd normally have to worry about, could it free up your mind to focus on the bigger, more creative parts of problem solving? It's a pretty interesting idea to think about.